We're going to do one more complicated example using Pascal's triangle. Here I have the quantity 2x plus 3 raised to the third power, and I've gone ahead and calculated out what that answer should be. I claim Pascal's triangle is hiding in this answer. Specifically, the third row of Pascal's triangle is in this answer. We are taking something to the third power, so therefore we are using the third row of Pascal's triangle. The third row of Pascal's triangle is 1, 3, 3, 1. Not only are all four of those components hidden in these terms, but I also claim 2x and 3 are hidden in each term. And that is a very important point because that's going to allow us to calculate these expansions quickly. And that's the heart of what's coming next. So here we go. 8x cubed is the first term of our answer. I'm going to rewrite that using the components 2x, 3, and one value from that row of Pascal's triangle. Since this is the first term, I'll use the 1. 1 times. Well, basically I'm factoring a 1 out of 8x cubed, so I'm left with 8x cubed. But I also claim that I can rewrite 8x cubed as 2x raised to the third power. And now I have a 2x and a 2x. I also can multiply that by 3 to the 0 power. And we know that 3 to the 0 power is 1, so we have not changed our overall value here. The next term is 36x squared. Second term, second entry. So I'm going to factor a 3 out of 36x squared. And when I do that, I am left with 12x squared. But I can rewrite 12 as 2x squared times 3 to the first. I can rewrite 12 as 2 squared times 3. And now again I have a 2x and I have a 3. I can factor out a 3. 3 is the next entry in Pascal's, that row of Pascal's triangle. I can factor 3 out of 54. 3 times, and when I divide 54 by 3, I get 18. But I can rewrite 18x really, as 2x to the first times 3 squared. That's 18x. And again, I have a 2x and a 3. And whoa, let's try that again. I'm going to slide these over a little bit. So I have a little more room here for my last term, 27. Pascal's triangle has a 1 in that spot. So I divide 27 by 1. Gee, that's 27. I have 2x to the 0 and 3 cubed. Let me slide that over just a little more. There we go. A little more room here. 2x raised to the 0, 3 cubed. And a couple of things I want you to notice. 1, 3, 3, 1. Here's 1, 3, 3, 1. There's that row hiding in our answer. Another thing to notice, 2x cubed, 3 to the 0. 3 plus 0 is 3. I have a third power. I have all three powers accounted for. 2x, 3. Again, the same two values that I had in my binomial appear in my answer. And now, here are my powers, 2 and 1. Again, they add up to 3. But notice what happened here. This power on the 2x dropped by 1. This power on the 3 rose by 1. And it makes sense that would happen, because if we look at our answer, we have something x cubed, something x squared, something x to the first, and here's technically x to the 0, which is 1. Well, if the x powers are dropping by 1, the powers on 3 should be rising by 1. And in fact, that pattern follows all the way to the end. Here's 2x to the first, 2x to the 0. 3 to the first, 3 to the second, 3 to the third, and so on. That is sort of what's happening behind the scenes of what is coming next. And what I'm about to show you is going to be probably the ugliest formula that you will see in your entire high school experience. But looks aren't everything. It looks bad, it looks nasty, it looks atrocious, but it is very simple to use. Here we go. It's called the binomial theorem. This was really explored in depth by Isaac Newton. It was kind of known before the time of Isaac Newton, but it really wasn't developed real well. Newton took this theorem and showed that it worked for virtually any kind of exponent you could put in place of n. It's a way to expand a binomial in full. We're going to stick to just whole number values of n, but understand that I could have n be a negative number, I could have n be a rational number, I could have n even be a radical. We could take this to a square root power if we wanted to. Newton showed that all of that is possible. We'll keep it simple and stick to n has to be a whole number. Here we go. Here is the binomial expansion, binomial theorem. It starts out with whatever a is, and notice a is just our first thing here, b is here. We could apply this to x plus 5. We could apply this to 7x minus 3 if we really wanted to. We have a and b in general. And our first term, a gets all the powers, b gets no powers. And b to the 0 is simply 1. Technically, there is an NC0 in front of a to the n. We know it's 1, so we don't need it. If there's an NC0 hiding here, and that's our Pascal's triangle entry, because look here, here's an N, here's a 3C0, here's a 3C1, here's a 3C2, a 3C3. Because we're using the third row, everything starts with 3C and then whichever spot we're at. Well, now we have NC something. And this is NC1. A gets 1 less power. B gets 1 more power. And we saw that in our last example. 3C1. A in this example is 2x, and it got 1 less power. B is 3 in this example, and it got 1 more power. It started at 0, it went up to 1. 2x started at 3 powers, it went down to 2. As I said, this is not a nice formula to look at, but it's quite simple to use in practice. Now we have NC2. A gets 1 less power than it did before, so now we're at n minus 2. B is now squared because it has 1 more power. Here comes NC3. A gets 1 less power again. B gets 1 more power again. How far do we go? We keep going until we get to NCN, which is just 1. A to the 0, and B getting all the powers. That's when we stop. So if we have a 5th power, this would be A to the 5th, B to the 0. 5C1, A to the 4th, B to the 1st. 5C2, A cubed, B squared. 5C3, A squared, B cubed. We'd have 5C4, A, B to the 4th. 5C5, which is just 1. A to the 0, which is still 1. And then B to the 5th. That's when we would stop. When we get to NCN and A having 0 as an exponent. That's our last term. That's when we're done. That is the binomial theorem. Had we looked at this without all the examples earlier, I think this would have been a little more difficult to follow. But with those examples in mind, it's actually not that bad to use. A gets all the powers, B gets nothing. Now I have NC1. 1 less, 1 more. NC 1 more. A 1 less power, B 1 more power. And so on and so on. Now there is an alternative form of the binomial theorem. If you take a math course in college, you take a statistics course someday, if you take a course in possibly discrete math someday, you might see the binomial theorem written like this. It's a little different form, but it means basically the same thing. There's our sigma for sum. We're summing from k equals 0 to n. This one starts at 0. And it's n choose k. This notation means n choose k. A to the n minus k, b to the k. Now what does this mean? N choose k. Well, it's something you've already seen before. N choose k is equal to n c k. So you've seen it. It's an alternate way to write a combination. K is 0. That means n choose 0. NC 0. Well, that's 1. A to the n minus 0. That's a to the n. B to the 0. Well, just b to the 0. And lo and behold, there's our first term. Now we go k equals 1. N choose 1. There's n choose 1. A to the n minus 1. Yep. B to the 1. Yep. This is just a shorthand of all this. And remember that the sigma means sum. Plus, 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 and add up all those terms. I'm not going to focus too much on this. I'm going to use the notation up on top because it's a little more practical for what we're going to use it for. Okay, example time. Let's use the binomial theorem. I'm not going to write out this entirely because we would have 11 terms. X to the 10th, something x to the 9th, on and on and on and on and on. But I'll start by doing a few, so we get a feel for what this is like. Our first term, x gets all the powers. So in about 1.5 seconds, we have the first part of our answer, of our final answer. No need to multiply out x plus 1, x plus 1, x plus 1 10 times. We've already got the first part of our answer. Next term, NC1, 10C1. X gets 1 less power. 1 gets 1 extra power. Next term, 10C2. X gets 1 less power. 1 gets 1 more power. And I'll do one more. 1 more, 10C3. X gets 1 less. B, or 1, gets 1 more. And that keeps going until we get to 10C10, x to the 0, 1 to the 10. So in approximately, I believe that was just over 60 seconds or so, we already have 4 terms of our final answer. Five, x to the 8th, 10C3 is 120, x to the 7th, and we have more terms after this, but in roughly a minute, 1, 2, 3, we have 4 terms of our final answer. That is the power of the binomial theorem. Without the binomial theorem, this is what you would have to do. You would have to multiply all of this out. And yes, I'm going to write all this out to show you just how long this would take. 2, 4, 6, 7, 8, 9, and 10. You would have to multiply all this out. In the time it took me to write those 10 quantities, we would be maybe here, 2 terms finished already, and I just finished writing this out. And then once we write all that out, now we got to start foiling. Well, I know what this times this is. It's x squared plus 2x plus 1, and then I do that again, and I'm going to end up with 5 of these. That's 1, 2, 3, 4, 5. And now I have to multiply these 2 together. And I multiply these 2 together. And then I multiply these 2 answers together. And then I multiply by that answer. And I'm still multiplying. And up here, we've already gotten 4 terms done of our final answer. By the time we get down to here, this answer is probably finished or pretty close. And by the way, when you multiply these together, you're going to get lots of things because this has to multiply by 3, this has to multiply by 3, this has to multiply by 3. So you get 9 terms. This will be 9 terms. And yes, some of those will combine, but the point is, you're going to have a big answer. You're going to here have x to the 4th plus cubed squared first constant, x to the 4th cubed squared first constant. Then you multiply those things together, so you get 16 terms. some of which are like, but still that's a lot of multiplication. Then you got to multiply that answer by this. Whew. That's a lot. Binomial theorem, we're almost half done in about a minute. Very efficient, very slick. Next problem. X plus 6 to the 8th power. And again, I'm not going to go all the way. I'll just do a few terms to get you started. X gets all the powers. 6 gets nothing. Now we have 8C1. There's the Pascal's triangle contribution. We're in the 8th row of Pascal's triangle. So here's our 8C1. X gets 1 less. 6 gets 1 more. 8C2. X gets 1 less. 6 gets 1 more. And that keeps going. So we start with x to the 8th times 6 to the 0. That's just x to the 8th. 8C1 is 8 times 6 is 48. 8C2 is 28. But now we have to multiply that by 36. And now we're up to 1008 x to the 6th, and we can keep going. You can see the numbers are going to start to get pretty big because the next one is 8C3 times 6 cubed. Give you a little spoiler alert. That's over 12,000. Then we're going to multiply 8C4 by 6 to the 4th. We're over 90,000. So you can see the values are growing very quickly as we move to the right. The further we go right, the larger some of those values are going to get. Let's look at another problem. This one I will take the whole way. I will do all the terms here. And also notice, now we have a minus. Don't be afraid of the minus. Do not be afraid of the minus. Follow the same procedure that you did before. But now you have to be a little careful with your signs. X gets all the powers. 5C1. X gets 1 less. I'm going to treat this as -3 gets 1. 5C2. X gets 1 less. -3 gets 1 more. 5C3. X gets 1 less. -3 gets 1 more. 5C4. X gets 1 less. -3 gets 1 more. And last but not least, 5C5 is just 1. X to the 0 is just 1. -3 gets all the powers. And now let's put this all together because this is not a final answer. We need to clean this up. X to the 5th. Yeah, no. Whoa, wrong button. Switch colors here. Let's go to this one. There we go. Something different. Now, before I put a plus, I got to look at my values. 5C1 is 5. But now I have -3 to the first power. And if you're not confident with your basic arithmetic here, this is going to be terrible for you. Negative 3 to the first is negative 3. So we have a sign change. We have minus. Negative 3 times 5c1, that'll be minus 15x to the fourth. Now we come over here. 5c2, which is 10, times negative 3 squared, positive 9. You cannot make a sign mistake here. You should know and have this drilled into your head that a negative number to an even power is always positive, period. I don't care what your calculator says. It's positive. So we're going to have a positive 90 x cubed. Because now we have a negative number to an even, the next one, negative number to one more, odd. This will be minus. And notice what's going to start happening here. We have plus, minus, and so on. That's going to alternate through this entire answer. 5c3 times negative 3 cubed. Because this term was negative, this next one will be positive. Negative number to an even power, positive. 3 to the fourth is 81 times 5c4. 5c4 is 5. And then our last term, minus 3 to the fifth. And there we have it. We have what's sometimes called an alternating polynomial because the terms alternate from positive to negative, and so on. Every other term is positive, every other term is negative. Yep. One final example. 2x plus 3 raised to the 7. Lots of mistakes have been made on problems like this because students do not pay attention to what they have. That is A. A is not 2. A is not x. A is 2x. That's what we're going to take to each power. So here we go, very beginning. A gets all the powers, but A is 2x raised to the 7. 7c1. Now 2x to the 6th, 3 to the 1st. 7c2. 2x raised to the 5th. 3 squared. And so on and so on. I will stop there. So make sure when you are calculating this out that you take both of these to each exponent. 128x to the 7th. Now we take 2 to the 6th times 7c1. Which that is not right because I didn't multiply by 3. I'm going to multiply by 3. That's better. Plus 7c2 times 2 to the 5th times 3 squared. and so on and so on. Be careful with that 2x to a power. Don't forget to take both components to that power. Don't just take x to that power. You take 2x to each power. Now, for purposes of assessment, I am not going to have you take 7 powers or 10th powers all the way out. The largest power I would have you go all the way on is a 5th. Would not, if you have to do one, if I give you a problem that says expand this, I will not go higher than a 5th power for all the way. Anything bigger than a 5th, I would probably say write the first 3 terms. So here's 1, 2, 3 terms. Or maybe write the first 2 or the first 4. Because if you can get it started correctly, then I assume you can finish it correctly. So there's no need for me to have you take something to the 20th power. I might just say write out the first couple. Besides, the higher I make the powers, the larger the numbers are going to get quickly, and that might overwhelm some calculators. So we'll keep it pretty small. As always, make sure you do your completion quiz for this section. Get it submitted in Google Classroom. And that is all for this one.